Today's video is going to be about polar coordinates. We're going to learn how to first plot a point in polar coordinates and then write three other representations of polar coordinates. Then second, we'll learn how to convert from rectangular to polar and polar to rectangular. And then we're going to convert equations from rectangular to polar and polar to rectangular. But in that transition of the equations, we're going to talk about how to identify what type of graph it is and write down its characteristics and attributes. So what you're going to see first is an exploration dealing with reviewing some different types of coordinate conversions. And so we have a right triangle given here with the legs X, Y, and R and the angle theta. And we're asked to write two things. We're asked to write an equation that relates X, Y, and R. And then we're asked to use trig to write equations for X, Y in terms of R, theta, or both. So we're going to start with the first equation, or the first part of this exploration. As you can see here, again, I mentioned we have a right triangle. The legs are X and Y, the hypotenuse is R. So you should recall from trig that to relate these three sides, we use the Pythagorean theorem. So we have X squared plus Y squared equals R squared. And you should be familiar with this equation because this is the same equation we've seen in unit circle trig. Part 2 says use trig to write equations for sides X and Y in terms of R, theta, or both. So we're going to start with X, which is right here. So X would be considered the adjacent side, and this is our hypotenuse. So we know that cosine deals with both adjacent and hypotenuse. So cosine theta would be X over R. And solving for X, we get R cosine theta equals X, which is true for any value of theta, and that's from, of course, vectors. We're going to take a look at now an equation that helps us solve for Y. So as you can tell, Y is opposite theta. And now we can use sine. So sine theta equals Y over R. And we solve for Y, we get R sine theta equals Y, which is also an expression we've seen before with vectors. And so we'll use these three equations to help us with polar coordinates. So first we're going to talk about what polar coordinates are. So polar coordinates are of the form R comma theta. So it's going to be a point where the first number is R, which is the directed distance from the pole. So this is the pole right here. And if you go X amount of units, or R amount of units, from the pole, you'll have that directed distance. And we'll talk about all of that in a moment with an example. What does it mean for R to be positive? And you can actually have a value of R which is negative. We'll talk about what that means. Theta is the directed angle measured counterclockwise from the polar axis to the line segment OP. So if you go counterclockwise, if you recall from unit circle trig, your angles increase in value until you get back to 0, to 2 pi radians. That's a full revolution or rotation. But if you go in the other direction, which is clockwise, your angles will decrease, but get more negative, and it will still make a full revolution, but it will be considered negative 2 pi radians. So with that said, we're going to go ahead and do an example talking about how to plot points in multiple representations. So as you can see on the screen, we have the point 3 comma pi over 4. And what we're going to do is we're going to plot the point, and then we're going to look for 3 additional points that represent the same point. So the way you plot a point in polar coordinates is you start with your angle, okay, which is pi over 4. So you're going to look for pi over 4 on your graph here. And you should know from your unit circle that pi over 4 is somewhere between pi over 6 and pi over 3. So we're going to say pi over 4 is here. And now we're going to go over to our value of r. As you can see, our value of r is positive 3. So that means we're going to go 3 units from the pole on the radial line, pi over 4. So we're going to count circles here. So 1, 2, 3. So there's where the point is. So the point 3 comma pi over 4 is right here. So now what we're going to do is look for 3 additional points that represent that same point, which is red on the screen. So our first point is of the form r comma theta plus 2 pi, which makes sense and agrees with what we've talked about with unit circle tree, because this is going to represent a point that is coterminal with pi over 4. And if you add 2 pi to pi over 4, you get an angle of 9 pi over 4. So here's our first representative point of 3 comma pi over 4, 3 comma 9 pi over 4. Let me convince you it's the same point. You're going to start with 9 pi over 4. As you can see, 9 pi over 4 is going to take you right over here to where pi over 4 is. So I'm going to put here 9 pi over 4. And our value of r is 3. So you're going to go 3 units. And if you notice, you get the same point there. So point 1 is equivalent to this point here. Our second point takes the form negative r comma theta plus pi. So we're going to make the 3 negative, and then we're going to add pi to pi over 4, which gives us 5 pi over 4. Again, I'm going to convince you that this point is the same point as the red and blue point. So we're going to go to 5 pi over 4. 5 pi over 4 is in quadrant 3. So I'm going to put 5 pi over 4 here. But r is negative. So r means go, this value of r says you're going to go 3 units in the opposite direction. So normally, if that was positive, we'll go 3 units here to pi over 4. But since r is negative, you go in the opposite direction, which puts you right back up here. So it's the same exact point. And another point, should be one more point, takes the form negative r comma theta minus pi. So we keep r negative, but we're going to subtract pi from pi over 4, and that gives you an angle of negative 3 pi over 4. So now we got to find where negative 3 pi over 4 is. So remember, since our angle is negative, we go clockwise from 0, and that puts you here at negative 3 pi over 4. But at negative 3 pi over 4, we're supposed to go negative 3 units. So normally we would go here, but because r is negative, you go in the opposite direction, which puts you back over here. So it's the same exact point. So we have 3 different representations. Well, actually, here with a total of 4, including this one, you have 3 additional representations for the same point. Okay, so now you should be able to try a couple of problems on your own. Here's one practice problem. See if you can do that on your own. Here's another practice problem you can do on your own. And if you have any questions about any information in this video, you're more than welcome to email me. So we're going to continue with the next thing about polar coordinates is converting from polar to rectangular. So if you notice here, these are the same equations we came up with earlier in the exploration. You have x equals r cosine theta and y equals r sine theta. So now what you're going to be asked to do is, you see these points here on the screen, you're going to be asked to convert polar coordinates to rectangular coordinates. So it's very important that you do remember your values from the unit circle. So let's start with -2, 5 pi over 3. So we need to write the rectangular coordinates for this. So we're going to utilize the fact that this is r, and that's theta. And so our first equation would be x equals -2 times cosine of 5 pi over 3. And if you actually simplify that, you get x equals -2 times cosine of 5 pi over 3 is 1/2. So you get an x coordinate of -1. And then we're going to do y, and that's -2 sine 5 pi over 3. And that's y equals -2 times negative square root of 3 over 2. That's the value at sine of 5 pi over 3. So y is going to give you positive square root of 3. So the rectangular coordinates for this polar coordinate is given as -1 square root of 3. All right, let's do one more. We're going to do this point down here, 1, 5 pi over 4. Process is the same. So x equals 1 times cosine at 5 pi over 4, which is given as x equals 1 times negative square root of 2 over 2. So we have an x coordinate of negative square root of 2 over 2. And then our y coordinate will be 1 times sine at 5 pi over 4. And that's y equals 1 times negative square root of 2 over 2 as well. So here we get y equals negative square root of 2 over 2. And so our rectangular coordinates for 1, 5 pi over 4 is given as negative square root of 2 over 2, negative square root of 2 over 2, excuse me. And so you can see here is just the use of using your parametric equations, because that's really what they are, x and y. And so now if you understood those two problems, you should be able to do these 3 problems here. Remember that all your theta values are in radians, and you'll need to know that information because number 3, you'll want to utilize a calculator. So for this third problem, you might want to consider using a calculator. So use a calculator in radian mode to get the corresponding rectangular coordinates for that point. So now we go to converting from rectangular coordinates to polar coordinates. Here we have r equals square root of x squared plus y squared, which is a derivation of one of the equations we came up with earlier in the exploration. And then theta equals arctangent or tangent inverse of y over x. So you'll need to recall the domain and range restrictions for the arctangent function here. But remember, here's the thing about converting from rectangular to polar. Rectangular to polar has multiple representations. just like we discussed in the very first example of how we can represent a polar coordinate in more than one way. So now we're going to take a look at these examples here. So the first example is 2, 2. So what will probably help is if you first plotted where the point is. So as you can see, 2, 2 is a quadrant 1 point. I'm just going to say it's right there. So I know my polar coordinate has to be a representation of a point in this quadrant. All right, so let's start with the fact that r equals square root of x squared plus y squared. So our x is 2 and our y is also 2 here. So r here would be square root of 8. And if you wanted to simplify that as 2 square root of 2, you're more than welcome to do so. But here I'm not worried too much about simplification. And I'm going to go ahead and label this point as x, y. So now let's take a look at finding theta, because that's going to be the tricky part. So theta equals tangent inverse of 2 over 2, which is equivalent to theta equals tangent inverse of 1. However you want to look at it. So what we want to do is find the angle on the unit circle between negative pi over 2 and pi over 2, because there is a domain restriction on that, such that my y and x divided gives me a tangent value of 1. And if you recall, that will give you theta equals pi over 4. So one set of polar coordinates for 2, 2 is square root of 8, pi over 4. And so what I want you to do, and I challenge you to see if you can find another representation of this point as well. You go back and look at the very first example to help you find other representations of this. Let's take a look at the second one. It's the point 0, negative 6. So again, we're going to plot the point. So 0, negative 6 is somewhere down here. It looks like it's on the axis. So that makes this problem just a little bit easier here. So let's do the more analytical approach. So we're going to find r. So r is 0 squared plus negative 6 squared. So pretty much what's going to happen is you're going to end up squaring the negative 6, which is 36, and then square root of 36 is 6. So r is 6. Our theta value is going to be negative 6 over 0. And we're looking for an angle that has a y and x coordinate when divided gives us negative infinity. Why negative infinity? Because our point is going downward. And so the point in the domain of the arctangent function will give you this value is theta equals negative pi over 2. And so one representation of these polar, one polar coordinate representation of this rectangular coordinate is 6 negative pi over 2. Now, some students are probably looking at this problem and said, why couldn't you use 3 pi over 2? That's actually another representation of this point. So 6 comma 3 pi over 2 will also be another representation. So remember, these polar coordinates are just one of many representations. So if you can come up with another one that's equivalent, you're fine. So using this information, you should be able to do the practice problems on the next page. Again, you might want to consider using a calculator. For the third problem, you want to use it in radian mode. Okay, so now we've converted polar to rectangular, converted from rectangular to polar. So now we're going to take a look at this from an equation standpoint. We're going to convert some equations from rectangular form to polar form. In order to do that, we'll need to utilize 3 of our basic equations. And I'm going to write them down here for you. It's going to be x squared plus y squared equals r squared. We're going to also have r cosine theta equals x and r sine theta equals y. So every time we see an x squared plus y squared term, we're going to replace it with r squared. Anytime we have x term by itself, we replace it with r cosine theta. And every time we have a y term by itself, we're going to replace it with r sine theta. So you definitely want to analyze the equation before you start just plugging stuff in. So let's go to this first one here. You have x squared plus y squared equals 16. Well, here our objective is to write this equation in polar form. And so we know that x squared plus y squared is going to be r squared. So far we have r squared equals 16. And if you solve this for r, by taking the square root of both sides, you get r equals 4. So that will be our equation in polar form. I'm going to slightly move this equation up. All right, so here we have 3x plus 5y minus 2 equals 0. And we're going to do some simple substitutions. So for every x, we replace it with r cosine theta. So we have 3r cosine theta plus 5 times r sine theta minus 2 equals 0. So now our objective is to solve for r. So I'm going to subtract 2 to the right-hand side of the equation. So we get 3r cosine theta plus 5r sine theta equals 2. And then you have a common factor of r on the left side of the equation. So we're going to factor that out. And then we're going to divide both sides by the expression in parentheses. So we get a polar equation of 2 over 3 cosine theta plus 5 sine theta. Okay, so this is going to take a little bit of algebra and creativity to try to get r by itself. I'm going to caution you, some of the equations you won't always get a nice expression for r. But again, the objective is to utilize the 3 equations you see here on the screen in purple. And then once you make those substitutions, manipulate the equation and solve for r. So with that said, you should be able to do these practice problems here. So again, make sure you understand what the 3 equations are and make sure you use them correctly. So now we get to the last part of the video, which is changing equations from polar form to rectangular form. This one requires a little bit more creativity, thought, and work. So what we're going to do is we're going to convert the equation to rectangular form using what we know. And then once we convert it, then what we have to do is identify the graph and write down certain characteristics of the graph. So this will require you to have some background knowledge about several types of conics and several types of functions that you dealt with from algebra. So let's start with the first one. We have the polar equation r equals 10. So I like to consider working backwards. And so what I'm going to do is I don't want r, I want r squared, because that's going to help me get the equations I want. So let me write down the three equations we used before. We have x squared plus y squared equals r squared. And we have r cosine theta equals x and r sine theta equals y. So for this equation, I'm going to square both sides. So squaring both sides of the equation gives me r squared equals 100. And then I'm going to replace r squared with x squared plus y squared. So you have x squared plus y squared equals 100. So there is the rectangular equation. Now we're going to identify the graph. Well, if you look at the form, this takes the form of the equation of a circle. So this is a circle with a center at 0, 0 and radius 10. So if the graph is a circle, you have to write down what the center is, and you have to write down what the radius is. All right, let's take a look at this one here. We have theta equals 5 pi over 3. Well, you could utilize these equations here. The issue becomes that you don't know a value of r, okay? So they really won't help you. So anytime they give you an angle, you want to take the tangent of both sides. So let's take the tangent of both sides. So tangent theta equals tangent at 5 pi over 3. So recall from unit circle trig, tangent theta is y over x. And tangent at 5 pi over 3 is negative square root of 3. And now we want to solve this equation for y. And if we do that, we get y equals negative square root of 3 times x. And as you can tell, this takes the form of a line. So this is a line with slope negative square root of 3 and y-intercept at 0, 0. So if the equation you get is a line, you must talk about what the y-intercept is and what the slope is. Let's move on to our next problem, which is a fraction. So we have r equals 1 over 1 minus cosine theta. So what I'm going to do first is I'm going to multiply both sides of the equation by 1 minus cosine theta. So if you do that, you get r times 1 minus cosine theta equals 1. I'm going to rewrite that again. So now we're going to distribute the r. So r minus r cosine theta equals 1. And so now we know that r is actually square root of x squared plus y squared. And r cosine theta is just x. So now using algebra, we're going to add x to the other side. X squared plus y squared, square root of x squared plus y squared equals x plus 1. So now we're going to square both sides to eliminate the radical. Let's square both sides. And if you do that, you get x squared plus y squared. Here you get x squared plus 2x plus 1. And then what we're going to do is we're going to subtract x squared from both sides, and you get y squared equals 2x plus 1. And as you can see, we only have a y squared term. There's no x squared term. So if you recall, that takes the form of a parabola. So this is a parabola. So I'm just going to come here and write it down. All right. And we're going to rewrite the equation as y minus 0 squared. And we're going to factor out a 2 on the right-hand side of the equation. So that gives us 2 times x plus a half. And so now we get more information about this parabola. So this parabola with an axis of symmetry x equals -1/2 and vertex -1/2, 0. Normally you would have to find the directrix and the foci, but here I'm not interested in those things right now. I'm just interested in finding the axis of symmetry in the vertex. Here's our next equation. It's r equals 2 over 2 minus cosine theta. And so the process is going to be the same. We're going to multiply both sides by 2 minus cosine theta. And that's going to give you 2r minus r cosine theta equals 2. Then we're going to replace r with square root of x squared plus y squared. We're going to replace r cosine theta with x. Then we're going to add add x to the other side. That's x plus 2. And then we're going to square both sides of the equation. So that's going to give you 4 x squared plus 4y squared equals x squared plus 4x plus 4. And now what you're going to do is you're going to subtract everything to the other side. And when you, subtract everything from the left side, from the right side of the equation to the left side of the equation. And so you're going to get 3x squared plus 4y squared minus 4x minus 4 equals 0. And as you can tell, this takes the form of an ellipse. And I know it's an ellipse because if you look at your x squared and y squared term, they're both positive, but they're not the same. If they were the same, it would be a circle. So we have an ellipse, and so we need to get the vertices, the center and the vertices of this ellipse. So what we need to do is we'll need to complete the square. So what I'm going to do is I'm going to group my x terms together. And I'm going to group my y terms together. And then I'm going to take my constant, which is -4, and add it to the right side of the equation. That becomes +4. So remember, to complete the square, you need your leading coefficient in each group to be a +1. So here we got to factor out a 3. That's x squared. That's going to give us a -4/3x. Now I always put a blank because I know I'm going to add something in there. For this, I can pull out the 4, but I'm not going to really have to do too much work in here because the y squared is by itself. And that's going to equal 4 plus 3 times something, because I factored out a 3 over here. So what I add over here, I got to add it over here as well to balance it. So to complete the square, you're going to take half of your middle term. So we're going to take half of -4/3, which is -2/3, and we're going to square -2/3, which is 4/9. So we add 4/9 in this blank here, and we're going to add 4/9 over here. And then we're going to factor. So we got 3, and factoring this expression gives us x -2/3 all squared plus 4 times y squared equals 16/3. And then what we're going to do is going to divide everyone by 16/3 because we need this to be a 1. So when I divide everybody by 16/3, actually, let me do this. Let me multiply both sides by 3. And so that's going to give me 9x minus 2/3 squared plus 12 times y squared equals 16. And then I'm divide by 16. So when I divide by 16, I get 9 over 16 x minus 2/3 all squared plus 3/4 y squared equals 1. But then I'm going to take the reciprocal of each of these, and that's going to give me x minus 2/3 all squared over 16/9 plus y squared over 4/3 equals 1. So there is the ellipse in standard form. There's the ellipse in standard form. So now we need to describe the ellipse. So in order to describe it, we need to first know what it looks like. So I can tell you it's what I call a horizontal ellipse. So what that looks like is I have an ellipse that's stretched like this. Okay. And I know that's a terrible drawing of an ellipse. I want to actually do this. There's an ellipse. A little bit skinnier. Okay, there you go. So there's the ellipse. And from this equation, the center is at +2/3, 0. And then I need to figure out what my vertices are. So I need these points here, I need this point, and then I need this point and this point. Okay. And so to get this, I need to find out what my radius is. My radius is the square root of this number, this denominator. So the square root of this is 4/3. So 4/3. Okay, so if I go 4/3 to the left of this, I get whatever that point is, excuse me. So so if I go this many units over here, that gives me a point, and I'll go that many units over there, that gives me the other vertex. And then if I go this way, I do this right here. So the square root of this is going to be 2 over square root of 3, which is not a nice number to have, okay? So it's an ellipse. With center 2/3 0 and vertices so pretty much what I need to do is subtract 4/3 from here, so it's negative 2/3 0, and then add 4/3 here, which is going to be 2 0, and then add this number here, so that's going to be 2/3 plus 2 over square root of 3. I'm sorry, I added to the wrong coordinate. You add that to y. So it's 2/3, comma, 2 square root of 3, and 2/3 negative 2 square root of 3. So those are your vertices. Notice a lot of work, but this is it brings back the conic piece as well. So you might want to go back and review conics and their attributes. All right, here's our last example we're going to do. Same thing. We're going to multiply both sides by our denominator, 2 plus 4 sine theta. So we get 2r plus 4r sine theta equals 3. And then you replace the r with square root of x squared plus y squared. And replace your r sine theta with y this time. And then what we're going to do is we're going to subtract the 4y to the right side of the equation. And then you're going to square both sides. So we get 4x squared 4y squared equals 9 minus 24y plus 16y squared. And then you're going to add everything that's on the right side, you're going to add or subtract it to the left side of the equation. And so you're going to get here 4x squared minus 12y squared plus 24y minus 9 equals 0. And as you can tell, your x squared term is positive, but your y squared term is negative. So that would mean this graph is a hyperbola. So now we're going to complete the square to actually get the true form of this hyperbola. So just like before, we're going to group our x terms together. So 4x squared goes over here. And then our negative 12y squared term goes here, plus 24y equals positive 9. We added 9 back to the other side of the equation. So now we're going to factor out our coefficients. 4 and x squared here. So we're going to we're going to factor out a negative 12. So negative 12, that gives us a positive y squared minus 2y plus blank equals 9 minus 12 times blank. Wherever we put here, we got to put here as well. So completing the square, you take half of this. Half of negative 2 is 1. And squaring the negative 1 gives you positive 1. Positive 1 over here. Now we're ready to factor. 4 x squared minus 12 times y minus 1 all squared equals -3. And we're going to divide everybody by -3. So that gives us 4x squared over -3. And then dividing the -12 by -3 gives us a +4. Y minus 1 all squared over 1 gives us +1. And so we need to rewrite this where the subtraction sign is in the middle. So we have, and we also got to get rid of the coefficients in the numerator. So what I'm going to do is I'm going to rewrite it and then take the reciprocal of the denominator, of the numerator, excuse me. So this is what I have. I'm going to have y minus 1 squared over 1/4 minus x squared over 3/4 equals 1. That is the equation of our hyperbola. And so the way our hyperbola is going to open, because y squared leads, it's going to open up like this. Open up like this. It's like two parabolas opening in opposite directions. So the center is here. So the center is at 1, 0. And then we got vertices here and here. And then you have asymptotes of the parabola. It goes through the center. I know my diagram is a little off. So you got an asymptote there, and you also have an asymptote here. They're supposed to go through the center. Like I said, my drawing is not the best drawing, but it'll do. I don't want you to get the gist of what we're trying to do here. Okay. So just pretend that this line right here, sorry about that, goes through the center. All right. So the radius is going to be 1/2. Okay. So it's the square root of this number is 1/2. So we're going to go, so from here to here is 1/2. That the distance from the center to the vertex is 1/2. So that point up there is really 1, 1/2. And down here, this point is 1, -1/2. That's our vertex. And our asymptotes are going to be the square root of b over a. All right. It's the square root of b, then the square root of a, and then you take the square root of b, square root of a, divide them, and then you use the center to write the asymptotes and point slope intercept form. So here's how we describe this parabola. So it's a hyperbola. I don't know if I said parabola earlier. It's hyperbola with center 1, 0, vertices at 1, 1/2 and 1, -1/2. Asymptotes We're going to be at y minus 0 equals, and pay attention to the slope. Let me go ahead and, since both of these are fractions, I'm going to have to take square root of them anyway. When I divide these two fractions, I'm going to get 3, and I take the square root of that, which gives me 3. So I got positive square root of 3 times x minus 1. And then the other equation is y minus 0 equals negative square root of 3 times x minus 1. Okay, those are the attributes of the parabola. Okay, I know that was a lot. So hopefully you have enough information to do some of these practice problems here. So again, make sure when you convert to rectangular form, make sure you are using the correct equations, first of all. Second of all, make sure you know what graph you're dealing with and know what attributes know the attributes of each graph. Okay. That will be the conclusion of this video. Here's some questions you might want to think about as we conclude this lesson. Make sure you can answer these and understand this part of the lesson of polar coordinates. My next video is going to talk about how to draw polar graphs using a calculator and without using a calculator, and using different attributes of graphs from algebra.